Okay, so we're starting the second part here, and this is about the geometry. So I just finished recording the part that talks about the Lewis structure. Now we're moving on to geometry. With geometry, we're starting with the Vesper. Chemists call this Vesper because it's so much easier to say in conversation. The Vesper theory. Anyway, Vesper, like it says right here, is essentially valence shell electron pair repulsion theory. It's a theory that's kind of self-explanatory, okay? Valence shell, this is the highest energy level in the atom. So going back to Bohr's model, remember Bohr's model talked about electrons being in different energy levels, okay? The other casual way of describing energy level is a shell. So it's like different concentric shells, small shell, big shell, and even bigger shell. So valence is the outermost, that's the nosebleed section, right? Like in the auditorium or a stage or whatever, the nosebleed section. So valence shell electron pair repulsion theory essentially says they're electrons that are usually existing in pairs. And these electrons are in that valence energy level, the uppermost, the nosebleed section. And what are these electrons doing to each other? They're pairs. This is where they're located in the valence shell, the outermost energy level. They're repelling each other, okay? And so we see this happening where around the central atom in the molecule. So this essentially, what we're going to be looking at from here until the end of the chapter is all about what's happening between these electron pairs that came from the valence energy level, and they're repelling each other, okay? So electron pairs repel each other in real molecules because they have the same charges, not personal. They distribute themselves in position around the central atom that are as far away from one another as possible. So they get in positions around the central atom, and these positions are very far away from each other as much as possible. They don't like to be close to each other. We thought we invented social distancing. No, these electrons are like, we have the same charge, stay away from me. It's not a 6 feet distance though. I feel like years from now, people will be like, huh, what is 6 feet distance? I'm hoping that they'll be like, huh, right? Anyway, the electrons do like to stay, they repel each other. So they kind of try to occupy positions where they're very far from each other. And in doing so, we get all these different geometries, right? The geometry is a result of the electron pair repelling each other. Okay, from that, we also get electron pair angle. This is the angle formed by any two electron pairs and the central atom, and then we get different shapes. So what I want to do right now is detour a little bit and talk about what are these said electron pairs. Okay, when we talk about electron pairs, we are talking about the following, okay? And remember, these are around central atom. So, okay, as I'm saying stuff, I'm thinking about what I'm saying. I'm kind of criticizing what I'm saying. So in my head, I'm thinking, wait, didn't I just say these electrons were located in the valence shell? Yes. In one atom, when you're looking at an individual atom, the electrons are housed in the valence shell, almost on the surface of the atom, right? Very close to the surface. But you have one atom's valence electron repelling another atom's valence electron. That's what we're talking about here. So atom on atom repulsion due to the electrons, right? Valence electrons. Okay. So electron pairs around the central atom, this is how we're going to be looking at it. One lone pair counts as a valence, as a electron pair, okay? And then the second one is a single bond. Remember, one single bond is made up of two electrons, right? So one pair of electrons. And the third one is going to be a double bond. Then the fourth one is going to be, triple bond. Okay? So these are called electron pairs. Down the road, these electron pairs will be called electron pair groups. So you want to be aware of that. Write this in your notes somewhere. It's very important because we will determine geometry and bond angles by counting these electron groups. So we have to know how to identify them. Okay? So while we're here, I want to simplify and talk about simplistic bond angles. So these are the different bond angles that we're going to be looking at. Bond angles within a molecule. So at the fundamental level, you guys are responsible for 3 bond angles. It's simply 3 bond angles, okay? In the first scenario, you have the bond angle that's 180 degrees. So you want to relate this to geometry. In geometry, 180 degree, this is the bond angle for a line. So this is usually the angle for a straight line. This is what happens when you record late in the evening when you're being gallivanting all day long, right? Okay, number 2, 120 degrees Celsius. Not Celsius, oh my goodness. 120 degrees. 120 degrees, this is an angle formed by dividing a circle into 3 equal parts. Okay, technically, the angle for the straight line is formed by when you divide circle into 2 parts. Remember, in geometry, the circle has a 360 degrees, right? Bond angle. The circle is 360 degrees. So if you divide it into 2, you get 180, which is half of 360. Divide the circle 360 into 3, you get 120, okay? So the third angle that we're responsible for is 109.5 degrees. Okay, if you're trying to follow the trend, right? When I was in school, the teacher was talking about this, and I'm like, oh, the third one will be 90 degrees. And then she said 109.5, and I'm like, hold up, where'd you get that from? I mean, this is follow the trend, right? Okay, here's the caveat. The first 2 are formed by dividing circles into equal parts, right? Into half and into thirds. The last one, though, you're not dividing a circle. You're dealing with actually a 3D figure. So it will be more like a sphere. And you're dividing this into 4 parts. And it's not really, what is it called? Slices, 4 parts like that. So with this one here, we get a tetrahedron. And the bond angle in tetrahedron is 109.5. So when I was in school, I was like, I am not going to remember this bond angle. Then, of course, I had this trailing mind. So I'm thinking, you know what? This reminds me of something. It reminds me of, this is way back in the days, right? Back at home in East Africa, Tanzania, where it was cool, right? This is when I was young, to have your favorite radio station. What station do you listen to? And it would be like 105.9, right? So sitting here in class thinking, this reminds me of a radio station. And I'm thinking, if I had a lot of money, I will hire somebody with a very deep voice. And then this is an if scenario, right? I was very rich, so it's not real, okay? If you go and Google the frequency for radio, 109.5 is not a radio frequency, okay? But this is a hypothetical scenario where I have lots of money and I hire this guy with a very deep voice. And so we pay for 109.5 frequency. And then he says, this is 109.5 FM. And everything he talks about is these corny chemistry jokes, and people who love chemistry tune in to listen. And it's so popular, right? I said, if I get it. When I teach this in class, people roll their eyes and look at me like, we can't believe this is a corny story. But let me tell you something. The purpose of the corny story is for you to engage. Even if you're dissing it, I don't care, because they never forget the bond angle. They forget 120, they forget 180, but 109.5, they never forget. You want to know why? There's a corny story attached to it. And I never forgot 109.5 FM. I had someone write 109.5 FM. I'm like, oh, it was just a story. Anyway, here are the bond angles, right? So the blue circle here represents the central atom. I know, I laugh at myself. And then here, these are the electron groups. You see them? They're bonds surrounding the central atom. Since we have 2 of them, the bond angle here is 180. Did I mention that here? Yeah, these bond angles also go with the number of electron groups, right? So I'll just show it right here. That's okay. When you have 3 electron groups surrounding the central atom, we have 120. 3 electron groups. This is 1, 2, 3. This is 1, 2. 120 is the bond angle. When you have 4 electron groups surrounding the central atom, 1, 2, 3, 4, 1 electron group, 2 electron groups, 3 electron groups, 4 electron groups, this has a bond angle of 109.5. Like the fake radio station for the guy that's has a very deep voice, is talking about all things chemistry. Okay. As an entertainment, not for study. Anyway, so to illustrate that, we're going through this here, and here they're talking to you about the electron pair geometry. So after these bond angles kind of stay away from each other, repel each other, they find a place where they're comfortable. And then because of that, we have all these molecules that have shapes that remind us of geometry. When you have a central atom right here, and the central atom is surrounded by 2 electron groups, they use the balloons here. These illustrate electron groups. The balloons here are illustrating electron groups. So what you're seeing here is apparently the central atom is somewhere in here. The 2 electron groups surrounded. These look like a line. So they're linear with a bond angle of 180, right? 2 electron groups. Okay. This one here, your central atom is somewhere here in the middle. It's hard to see, right? But it's surrounded by 3 electron groups. And this tends to form what is called trigonal or triangular. Either word is appropriate. You can use one or the other. I tend to use trigonal more because I see more books use trigonal. But if you prefer triangular because you can relate to that triangle 3 sides, that works too. Trigonal or triangular and planar. This part here, planar, is very important. Please don't skip the trigonal part and write planar, because it's more than, we are only covering 3 main geometries, the 2 electron groups, 3 electron groups, and 4 electron groups, but there's technically 6. We're not covering 5 and 6. And 5 and 6 have other shapes that end with planar. So don't just skip this part and write planar like I know what you're talking about. Okay? Don't do that. Write trigonal or triangular planar. I'm referring to your lab work. Okay? You can't just use planar because there are other shapes that have the word planar too, and they're different from this. Okay, but planar here means flat. The name, once again, is trigonal, planar, or triangular planar. Okay, that describes 3 electron groups that are flat. When you look at them on the side, the center is right in the middle, and then you have these 3 bonds coming from the center. And the center is not raised, it is flat. Okay, because in some of your homework, they have you take the molecule and look at it in different angles. And if the center in the middle of the triangular planar is raised, that's not triangular planar anymore, because the central atom and the surrounding atoms are all on the same plane, ergo planar or flat. Okay, that's what that means. Okay. Moving on over here, we have tetrahedral. Tetrahedral is similar to the tetrahedron, the geometric figure that looks like this. Okay, so with this one here, the central atom somewhere in the middle, surrounded by 4 groups. Okay, so picture this, right? This is me. I'm young and I'm learning this back at home in East Africa, Tanzania, and I'm learning this and I'm like, I can't relate to a tetrahedron. We hadn't talked about that in geometry. And I'm trying to think about something. So I call this a chicken foot. That's just my word for it. This is not, the teacher didn't use it in the curriculum. Because when I saw the teacher draw it, I'm like, this reminds me of a chicken foot. That was my thing, okay? Listen, I was trying to survive chemistry, and I had to relate to this stuff one way or the other. Nobody asked me what to call this, so I just called the tetrahedral. Every time I saw it, it was a chicken foot, and that helped me do better, okay? By the time I was in college, I was getting A's. So I'm just saying. Not in middle school, I was still figuring it out though. But anyway, I call this a chicken foot. Now since we're in America, you might not relate to that. I would say visually, it looks like a tripod stand. So a tripod stand, right? With the 3 legs, and then you have the actual stand part. That's what it looks like. The bond angle here, 109.5. So when you have 4 electron groups around the central atom right here, 4 electron groups, the bond angle is 109.5. So hopefully you can remember that. Then we have this whole table right here. So this table here, what this is showing you is variations of what we're looking at. So let's see. I do have some notes here. And essentially, this chapter is going to be ending pretty soon. Even though it shows a lot of slides here, this is kind of going through all the different details. But I'm going to be ending this really soon. So what I'm going to do here is, let's see. 1, 2, 3, 4, 5, 6, 7. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yikes. 1, 2, 3, 4, 5, 6, 7. Okay, let me see if I can insert this right here. I'm going to try to talk about this, but I want to insert a table. I'm going to add a page here and see if this works. Yeah, this is something different I'm doing. So let's see if that works. Table template. Ooh, okay. Can I do a table? I'm trying to do a table, but I need a grid. A grid can count as a table, right? Yeah, yo, I'm making this up as I go. So 7. Okay, let's see if that will work. Done. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Oh. Okay, let me see if this will work. So here I have Lewis structure. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, this is not going to work. I need more columns. So let me see. Can I go back? That was neat. You know, you put yourself out there and you try something new and then you can improve upon it. So I need more columns. I need 9 columns. So let me see. Yeah, they made updates on this. So let me see. Template, because it's not really a table. It's this right here. So I need 9. Let's just do 10. This right here. Okay, done. See, I keep requesting more, but then it's not doing it. 1, 2, 3, 4, 5, 6, 7. I guess it can't do anything smaller than what I'm requesting, right? Huh. Okay. Let me try to do what I can do right here. Lewis, structure. And then here I have, oh, sorry. I need to go back. So back here, I'll do the formula. Lewis, structure. Number of bonded groups. Now the context here is around central atom, okay? That's the context. I just can't. Okay. I just can't write all those words. Maybe I should write a little smaller. Hold on. Number of bonded groups. Oh, it's electron groups. Electron groups around central atom. Number of lone pair groups around central atom. Okay, I left the electron part out there, but you know what I mean, okay? And then here, what do I have? So I have this, I'll say electron pair geometry, molecular geometry, okay? And then I'll say here, molecular type. So what I'm gonna do when I'm done working on this, I'm gonna actually get one. Wait, I don't need all this, do I? This is visible enough, right? Okay, I'm assuming this is visible enough because, yeah, molecular type. What I'm going to do is when I'm done with all this. Okay, so what I'm going to do now is create this table. This is going to be similar to the one that's provided. Oops, where is that? Right here, okay? So I'm going to have my Lewis structure here. Oops, hold on a second. My Lewis structure here. I'm going to have my space to write, but you want to create something similar in your notebook. So your Lewis structure here. And then let's see. After my Lewis structure, I want to have my total. I'll write EG to stand for electron groups because I don't have a lot of space. Okay, total electron groups. And the context here is that the electron groups are around central atom. Okay, the context, like I mentioned before, we care about the electrons that are the electron groups that are around the central atom. The ones that are in contact with the central atom. The ones that are further away, we don't care about. Okay, when they say around here, they mean, well, this is a U and this is an N. In contact with. Okay, so that's very important. And then of the total electron groups, we have number of bonded electron groups. These are the electron groups that are bonds, and then number of lone pair. Let me see if I can write this here. Write this real small. Lone pair electron groups. Okay, maybe I can write one is like this. Okay, hold on. Because I had these zoomed out, so it was hard for me to write. Bonded electron groups. Okay, then after that, I have, let's see, I want to do electron pair geometry. Okay, after that, I want to do molecular geometry. And then from here, we will do molecular type. And then we'll do bond angle. This is the angle between the bonds. Bond angle. And then finally, we'll answer the question, is the molecule polar or non-polar? And this will essentially cover the remainder of the chapter. Okay, so to make sure I'm actually recording this. Yep, I'm recording this. You can hear the audio and then you can see me. Great. Okay, so the first one, the formula that we have in the table provided was BeF2. Then we have BF3. We have SO2, CH4, NH3, H2O. Okay. Okay. So BeF2, right? So beryllium is in group 2 and we have one of these. Fluorine is in group 7 and we have 2. So this is going to be 14. This is going to be 2. We're working with what? 16 electrons. Okay. So beryllium is in the middle. We have a single bond, fluorine. I'm going to go through this real fast. So -4, we're left with 12. We got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. -12 equals 0. So this is our Lewis structure right here. So what I'm going to do for this is take this Lewis structure and then bring it all the way over. Did it fit? Over there. Okay. So all of this was just a means to an end. There's my Lewis structure. To finish this table, you have to have a Lewis structure. Now I'm beginning to think I should make this vertical, right? So this next one here is BF3. With BF3. Once again, we got boron in group 3. We got 1, which is 3. We got fluorine, which is in group 7. We got 3, which is 21. You add these two, you get 24. You got boron in the middle, you got fluorine, you got fluorine, you got fluorine. Oh, by the way, if you're wondering why I didn't double bond beryllium, beryllium is before carbon. Carbon is the first one that achieves octet. So any element before carbon, you do not double bond, right? Where was I? Boron is right here, single bond, single bond, single bond. It uses up 6 electrons. We're left with 18 electrons here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 3 is 18. We're left with 0 electrons. Okay. Can I move this over there? Can I make it really small? We'll find out. Oops. Oh, come on. They have this touch point limit. Can I squeeze it in there? Oh, it made it. Okay. So hopefully y'all can see this, right? It's kind of hard for me to. Yeah, that's the structure right there. And I'll try to zoom in when I'm working on it. SO2, let's see. SO2. Sulfur is in group 6 and I have 1. Oxygen is in group 6 and I have 2. So this is going to be 6, this is going to be 12, this is going to be 18. Sulfur, 2 oxygen, single bond, minus 4 equal 14. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 2 is 12. We're left with 2. Put the 2 dots here. Minus 2 equals 0. Okay. Gotta help the oxygen the sulfur get to octet. So take the 2 electrons off from here and double bond this, and we have our structure. So let me see. How do I make this? Oh, this is lopsided, right? That's okay. I'll move this and then I'll try to draw the dots in when I get here. Okay, dot, there. Okay, yeah, we needed some dots there, some dots here. That's our lowest structure. Okay, CH4. I did CH4 before, right? So I won't draw it again. I won't go into details. CH4 is going to be C, H, 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 H. Then NH3, I did that before too. NH3, this is going to be N, lone pairs, H, H, H. This may be a better way to do it. H2O, H2O. H2O is going to be H, O dot, 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 H. Okay. Let me see if I can redraw this. B, F, 1, 2, 3, 4, 5, 6. F, 1, 2, 3, 4, 5, 6. F, 1, 2, 3, 4, 5, 6. That's maybe better. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so hopefully this can be seen a little better. The next thing I'm going to be working on, let me try to make this all separate. Next thing I'm going to be working on is the total number of electron groups around the central atom. I'm going to count them all. I won't separate one from the other. So this is 1, 2. I have 2 electron groups, right? On this one here, I have 1, 2, 3. I have 3 electron groups. It doesn't matter what they are. I'm just using the rule of identifying what the groups are. Over here, oops, sorry. This is 1 electron group. This is another electron group. Oh, what happened to the lone pair that was here? Somehow it disappeared. Supposed to be a lone pair that was there. Okay, I should have 3 electron groups here. 3 electron groups total. Maybe I forgot to write it down. Okay, over here I have 1, 2, 3, 4 electron groups, right? 1, 2, 3, 4 electron groups. It just says total, doesn't say separate the bonding from the non-bonding ones, just total, 4 electron groups. And here I have 1, 2, 3, 4. These are 4 electron groups. So if you look at the order here, I have 2, I have 3, I have 3, I have 1 of the 2s, 2 of the 3s, and 3 of the 4s. In 1405, we're only doing up to 4 electron groups, but in the majors class, it goes all the way to 6 electron groups. Okay, and then next it says number of bonded electron groups. So of those bonded electron groups, we want to find out which ones of all the electron groups. We're trying to find out which ones are bonded only. Okay, so for this one here, let me use a different color for bonded. Green. Is green okay? Okay. So the green will be for the bonded, right? So both are bonded. Do I have any non-bonded ones? No. So there are 0 dots or lone pairs in the central atom. Here, let me see. Other groups I have, which ones are bonded? All 3 that I saw. See? 3. How many lone pairs in that formula right there? 0. See that? Okay, let me zoom this in a little bit so you all can see. Okay. In SO2, I have two groups that are bonded groups, right? But then I have one that is still yellow. That's a lone pair. So I put 1 here. So this is going to be 3, 2, 1. When you add the different types of groups, you get the total groups, electron groups around the central atom, right? Down here, this is a bonded group. This is a bonded group. This is a bonded group. So I have a total of 4 bonded groups. And in those groups, none of them are lone pairs, okay? In NH3, I only have 3 of the groups I highlighted before that are bonded groups. And there's one that I didn't highlight again because that's a lone pair group. Let me see. In water, I have 2 bonded groups. And then the 2 lone pairs that I didn't highlight. So 2 bonded groups, 2 lone pairs, okay? So hopefully this will help you guys in your lab as you're working in your lab. Because the geometry you pick has to be consistent with the number of bonded groups you have, right? Okay, so as we're working on figuring out the electron pair geometry, please know that the electron pair geometry that you're using matches the molecular geometry if there are 0 lone pairs. What do I mean by this? Okay, let me actually draw this across. I'm trying to make a table out of this. Y'all can see that, right? Okay. I don't know why it has to be a complete table, but we're getting there. Okay. So since I have 0, since all my surrounding groups, my electron pair groups around the central atom are bonded groups because these numbers match, and there are 0 lone pair groups. Since these are 2 groups, the name of the geometry, electron pair geometry, is linear. That is the same name we have for the molecular geometry. Please notice molecular geometry is also called the shape of the molecule. In the shape of the molecule, all we really care about is the bonded groups. Okay, so I'm going to write this somewhere. I wrote here, I need the space to write something else as you guys are taking notes. Molecular geometry is influenced by lone pairs, but depends on bonded groups only. We have our Lewis structures. We have figured out total electron groups around the central atom, right? We've counted them and highlighted them. We figured out which of those groups are bonded groups and how many of the bonded groups we have in each structure, and they're all written here. We have figured out how many of those electron groups are lone pair. Remember, lone pair are those dots, right? And these are written down. From here, essentially, the total electron groups ties into the electron pair geometry. So let me go ahead and highlight these the same so you can see what the connection I'm talking about. The total electron group influences the electron pair geometry. Then in the end, where was I? Let me find a different color. Can I use this blue? The number of bonded groups will influence the molecular geometry. So that's how they influence each other, okay? Let me go back to the regular highlighting color, which is yellow. Okay, so based on this number here, if you have total of 2 electron groups, the electron pair geometry you have is gonna be linear, like the balloons, right? 2 balloons are gonna be about 180 degrees away from each other. Moving on, when you have 3 electron groups, regardless of what the groups are, the electron pair geometry will be trigonoplanar. Since the electron groups here, total electron groups are the same, this is still going to be trigonoplanar. Okay? When we come to the 4 electron groups, because these total electron groups are 4, this would be tetrahedral. I need a little bit more space. tetrahedral. So I'm writing diagonally, tetrahedral, okay? Because remember, the 4 electron groups, regardless of what the groups are or the nature of these groups, yields electron pair geometry that's tetrahedral. It's just telling you how spaced these electron groups will be from each other. What angle will they have, right? They will space each other. They will kind of rearrange themselves to have the tetrahedral geometry. Okay, when it comes to the shape, though, things are different. In this shape, what we are considering is the shape we see when we only look at the bonded groups, not the bonded groups, the lone pairs. So in this first shape here, you have a central atom surrounded by 2 other atoms like that. So that looks like a line, so that's going to be linear. Please notice, the electron pair geometry matches the molecular geometry as long as we have 0 lone pairs on the central atom, okay? So I can say here, we have 3 electron groups, all 3 are bonds, so this is going to be trigonal planar. Same name as the electron pair geometry. Why? We have 0 lone pairs. Then here is going to be different. But let me skip on and talk about the ones that all have the same geometry as the electron pair geometry. Because we have 0 lone pairs here, this molecular geometry is called tetrahedral. Same as the electron pair geometry. Now let's look at the shape of this molecule. So I'm going to go back. Trigonal planar looks like this, right? But now we're told that one of the electron groups is not there. Instead, is replaced by a lone pair. But remember, when it comes to looking at the molecular geometry or the shape, we ignore the lone pair. The lone pair keeps the shape, the bonds that remain in a V shape, but we don't consider that. So anytime you see V shape, this is what I picture in my head. Chemists said, well, it's not really a line. No, it's bent. Yeah, let's call it bent. So they call this geometry bent. When you have that V shape because the third group is missing, it's called bent. Okay, versus a straight line that's called linear. Okay, starting with this group right here, the chicken claw tripod. The tripods or tetrahedral geometry, you have all 4 groups present, right? But in this next scenario here, 1 group is missing. So I'm going to remove the group so you can see. The top group is missing and it's replaced by just the top group, sorry, it's replaced by the lone pair. Now remember, in the shape of the molecule, we pretend the lone pair is not there. So the shape that remains is this bottom shape. So you're looking at it saying, this reminds me of a pyramid. Yeah, a pyramid, but not just any pyramid. A pyramid with a triangular base. So guess what? Trigonal pyramidal. How is this different from the planar? In the planar, the central atom is in the same level as the surrounding atom. The trigonal pyramidal, the central atom is raised above the surrounding atom. So it looks like a pyramid, okay? Okay, and then finally, let me continue with that. So we got this. Then finally, in this last step here, we got this situation. So 2 of the bonded groups are gone, replaced by dots, lone pairs. But we don't care about the lone pairs when it comes to the shape, right? All we care about is the shape formed by the bonds. The bonds are forming, once again, we recognize that, a bent shape, like we saw up here. Remember up here, we had the 3, and then we had the bent. So we see the bent shape again over here. And so this is going to be bent. And that's all we're going to be covering in 1409. So we got bent, that right there. Hopefully this helps you with you guys' lab. Now we're looking at the molecular type. Okay, so the molecular type is really not that bad, but people mess this thing up. Now I think in your lab, the letters they use is ABL. Okay, I'm going to stick with the one that's in the PowerPoint. Let me see. Let me go back up here in the PowerPoint. This one is AB what? Oh, I didn't realize I didn't have anything for the, oh, snap. I'm just not realizing. Okay, anyway, I'm going to use ABL here. Molecular type, which is ABL. Okay, But let's say ABE, because I think your lab may be ABE. Some books uses ABE, some uses ABL, but let me interpret what these letters stand for. A stands for it's a generic way of representing the central atom. Okay, so A stands for central atom, and then B is the other atom or the surrounding atom. It doesn't care, just in general, surrounding atom or the other atoms. And then E stands for lone pair electrons. So each of these dots here count as 1E. And you want to count and consolidate, okay? So in this picture right here, the central atom is represented by A. We usually have 1A. And then each of the surrounding atoms is B and B. Since the central atom does not have a lone pair, there's no dots here, all I have is A, one central atom, two surrounding atoms is going to be AB2. Okay? For my next one here, I have one central atom, three surrounding atoms. So when I consolidate, once again, no dots on the central atom. We don't care about what's happening on B. I get A, B, 3. On this one right here, central atom S stands for A, surrounding atom or other atoms are B, and then on the central atom we have one lone pair, which is going to be E. So when I write this down, I'm going to consolidate. I have one A, I have two B's, and I have one E. A, B, 2, E. On this one here, central atom, I have one. I have 4 surrounding atoms, and so I end up with A, B, 4. On this one here, I have a central atom, A, 3 surrounding atoms, B, and then this one lone pair here, E. So I end up with A, B, 3, E. So you see how that goes? You're kind of consolidating. And over here, on the oxygen is A, and I have B here. Oops, no. B here, central one, each lone pair is an E. So this ends up being A, B, 2, E, 2. Now, some books use L in the place of E. Some books use X in the place of B. So it can be ABE or AXE or ABL, whatever it is. Just don't mix them up because then you get confused and you won't know what you're doing. So I use ABE, so just go with that, okay? Or you can use the equivalent in your lab. Okay, bond angle. When we have 2 electron groups, our bond angle tends to be 120, right? The angle between the bonds. Sorry. Oh, man. My mind is going somewhere else. My mind's already on the next one. My bad. Sorry. 2 electron groups, bond angle 180 degrees, right? 3 electron groups, bond angle 120 degrees. And if it's going to be 3, these 3 right here, I shouldn't focus on that. These are the 3 that form in the bond angles. Now remember, in the band, your bond angle is still 120. Now in the majors class, we learned that the lone pair makes the bond angle slightly less, but you can just write 120. 120 should be sufficient. In the 4 electron groups, your bond angles are 109.5 FM. 109.5, 109.5. In the majors class, we learned that the presence of the lone pair alters the bond angles a little bit, but for you guys, 109.5 is sufficient. Okay. Guys, we're about to be done. And once we're done with this table here, we're going to be done with the rest of the chat. Well, I'll kind of skim through the rest of it just to show you how we get to the end. Okay. Polar, non-polar is like a whole different section in and of itself. Okay. So I have to define some rules. Let me kind of detour a little bit to add some to the rules, and then we'll come back to this page right here. Okay. So to tell if a molecule is polar, remember polar stands for different. We talked about different atoms, right, within a bond. Now we're talking about molecules that are already built and whole, but there's differences in the molecule. To tell if a molecule is different, number one, you have to have, let's see, it helps to have different elements. So you have to have elements with different electronegativity. Okay, so if you have significantly different elements, that might set you on the path of having a polar molecule in the end. Okay, number 2, it helps if you draw Lewis structure and look for the following. So you want to draw the Lewis structure because you're trying to look for the following. A, different surrounding elements. Okay, so let me write this differently. Actually, what I meant to say is surrounding elements that are different from each other. Okay, so you want your surrounding elements to be different from each other. I need to add a lot of pages here. Different. It's all about getting all those pages, right? So if at this point here, I sing the song, one of these things is not like the other, right? One of these things is not like the other. If you have surrounding elements that are different from each other, you're most likely going to have a polar molecule, i.e. polar. Why? You have a difference or different. And then the B is if central atom, how do I end up writing diagonally? That's the time. Is surrounded by different electron groups. The one that we're looking for here is usually a lone pair. If lone pair is present, most likely polar. Okay, so 2 things we're looking at. If the surrounding elements are different from each other, you have a polar molecule. Essential atom is kind of has lone pairs on it. We have a polar molecule. So let me go over here. I'm going to highlight with pink because I need this to be shocking. Pink, the molecule that is polar. And of course, if those rules are not obeyed, then it's going to be non-polar, non-difference, right? So look at this one here. Fluorine matches fluorine, right? The surrounding molecules or the surrounding atoms match. And there's no lone pair in beryllium. So this is going to be non-polar, no difference. What about this one here? The 3 fluorines match, and there's no lone pair in boron. This is going to be non-polar. Oh, how boring. Oh, exciting. The oxygens match, right? But we have a lone pair on the sulfur, so we do have a difference there. The difference makes this polar. So let me highlight what part makes it different that makes it polar. This part here, the lone pair. Okay. And then here on CH4, all the H's match, all the bonds match, non-polar. No difference. Here, look at that. We have 3 bonds, but 1 lone pair. That lone pair makes that polar. And then with water, come on, very polar. Water has 2 lone pairs right here, and so this is going to be polar. Wrong writing utensil. Polar, right? We have a difference in the electron groups. So essentially, I have finished this table right here. Feel free to stop, rewind, watch over it again. I've had a long day of recording and a long day of activities because Christmas is tomorrow. I'm trying to get this out because my other recording just died. It didn't die. Well, the class got archived, so we don't have access to it. I didn't realize I was gonna lose access. Okay. So here are the rules. Please feel free to review. And then here they're showing you how to get the molecule in 3D. If you're drawing the molecule in 3D, it just shows you here that the wedge just means the bond is coming towards you, so it looks more, you know, that the effect when you're taking a picture and you want something to look bigger, So you kind of put your hand out, and then your hand looks proportionally bigger than your head. So in this case, the bond, if you have a wedge, like say you have CH4, and you want to show this as 3D, you make one of the bonds a wedge, and then this is considered coming towards you, right? Like that photograph effect. And then you make another one like this. It looks like dashed lines, so you have a dashed lines. The dashed line is kind of like astigmatism, where it's blurry, so you can't see very well because it's far away from you. And then two other lines are solid lines like that, H, H. So this is considered flat. This is considered 3D. If you want to draw 3D in a 2D surface, but communicate 3D, okay? So here are the rules of predicting the molecular geometry. I've gone through all the stuff. Feel free to read this at your own time. I talked about wedge and dash. This is showing you trigonal pyramidal because the central nitrogen is raised from the rest of them, and it's showing you the 3D geometry. And this is trigonal pyramidal, okay? It does reflect the tetrahedral electron pair geometry, but this right here is the shape, okay? And so I went through all of this showing you the different geometries. If you do have an organic molecule like this is an organic molecule because it has carbon in here, bonded to other elements. If you have a scenario like this, where you have obviously two central atoms, what you want to do here is assign one central atom first, then assign the next one, okay? So for this as a central atom, we have one carbon here surrounded by, let me change the color here, 3 groups, where all groups are bonded groups. So, and they're flat, right? It's 3 groups. So it's gonna be trigonal planar. If they ask for a bond angle, 120 degrees. Same thing with this. We got 3 groups, 1, 2, 3. All 3 groups are bonded groups. So this is gonna be trigonal planar, right? So essentially we have 3 groups, all 3 are bonded groups, 0 lone pair. 3 groups, all 3 are bonded groups, 0 lone pair. So I'm looking for 3, 3, 0, right? Let me go back here to the table I just drew here. I'm looking for 3, 3, 0. 3, 3, 0, trigonal planar, okay? And all the other stuff that you need should be right here, 3, 3, 0. So you can use the table as not really a cheat sheet, but a way for you to figure out the geometries. In this case here, well, I can use the table, right? I got 1 group here, that's a lone pair, 2 groups, 3 groups, 4 groups. So I got 4 groups where 3 are bonded groups and 1 is a lone pair, right? These 3 are bonded groups, 1 is a lone pair. So I'm looking for 4, 3, 1 in my numbers. 4 groups, 3 of them are bonded groups, 1 is a lone pair. The name of this shape is trigonal pyramidal, okay? So you can use that method to figure out what the geometries are. Okay, so I've done that. I've done this one here. I'm kind of just skimming to the end. I've done polar molecule, showing you how to figure that, polarity. Oh, they do that here. So we're looking at this CO2. In CO2, you essentially have carbon, lone pair here, like that. The central atom has got this surrounding atom matches that surrounding atom. There's no lone pair here. This is going to be non-polar. And it says here, no dipole moment. That means it's non-polar. Of course, this is right here is water. So you have oxygen, hydrogen, hydrogen. We have 2 sets of lone pair. So with these being different from the bonds, this is definitely polar. When it's polar, you have a net dipole, okay? And this is showing you, once again, we have carbon, we have hydrogen, hydrogen, hydrogen. The bonded groups are all alike. The surrounding groups are all alike. This is going to be non-polar. This one here is not like the other. This is going to be polar. These 2 are not like those 2, the surrounding groups. So this is going to be polar. This one here, these 3 are not like that one. So this is going to be polar. Now here, all 4 are alike again. So it's going to be non-polar. no difference, right? And it shows in the net dipole here. You can read it into that. We're not going to be doing much with that. And then we finally end on organic chemistry. In organic chemistry, this is a chemistry where we're seeing how carbon is bonding with other nonmetals, okay? This is usually carbon bonding with nitrogen, oxygen, fluorine, hydrogen in big, large molecules that are naturally seen in nature. So it's called organic, okay? And they give you some examples here. So I'm just going to skim over it. With organic compounds, I want to talk briefly about hydrocarbons. Hydrocarbons are compounds that have hydrogen and carbons only, okay? And these are organic compounds that have hydrogens and carbon, and then the carbons tend to have a single bond. So I'm going to skim over this part real quick just to show you that these are carbons bonded to hydrogens, and all the carbons have single bonds. They're showing you isomers here, okay? All of these molecules have the same number of carbons. They all have, at least the ones on the left have 4 carbons, so C4. Then they have 10 hydrogens. So both of these structures here, though they look different, have the same number of carbons and hydrogens. On the right side, we have 5 carbons and we have 12 hydrogens. So these 3 structures here, they're called isomers of each other because you have the same ingredients, essentially, the same elements combined, connected differently. So these Lewis structures are all valid, like we mentioned before, but they make molecules with very different characteristics, okay? So I won't go into the alcohol, the ethers, and the rest of these because there's a whole chemistry class where we focus on this, but you want to recognize something, at least in drawing these. In all of these organic structures, the carbon has got 4 bonds, right? Remember, it was this combination where all the bonds are single, or the combination where 2 are double and then 2 are single. 2 are together and then 2 are apart. Or the combination where 3 are together and 1 is apart, like that. I'm trying to think of what, or 2 are together and 2 are together. Yeah, the carbon can have these configurations right here. The hydrogen is simple, single bond, right? We mentioned this before. So you have this right here for hydrogen. You have this right here for carbon. You got that, you got that, you got that, you got that. When you're dealing with oxygen, oxygen looks very different. With oxygen, you have oxygen single bond, lone pairs, or oxygen double bond and lone pairs like that. So you have that combination for oxygen. Let me use a different color. Orange for oxygen. Just making this up as I go. And then we have nitrogen. I'll write that down here. Nitrogen has 3 bonds and a lone pair. Nitrogen has 2 bonds and a single bond and a lone pair. Or it can have nitrogen with 3 bonds and a lone pair. So all of these are common combinations of these elements, and you want to be aware of them, okay? You tend to see them a lot, like that, like this, like that, okay? So here you have different combinations of that. The carbon having one of these combinations as it fits, in ethers, and there's a whole, if you take Chemistry 1407, I go over this in details. Right now, I feel like it's out of context and it's not very meaningful, but ether is used in biology, usually to sterilize or to knock out. Because I remember watching some movies, murder mysteries, where someone was knocked out with ether, okay? Of course, we know about alcohol, drinking alcohol, or rubbing alcohol for cleaning and disinfecting wounds. Remember how alcohol disappeared last year in the year 2020? Alcohol and toilet paper, right? For carboxylic acid, the example here is vinegar or ascorbic acid, vitamin C, or salicylic acid, aspirin, or what else? Many citric acid, oranges, right? So yeah, this is just an FYI. These are different functional groups. I'm not going to go more into that here because there's a whole class where we cover this. We cover more relatable chemistry, right? Where it's not the theoretical fundamental stuff, but more chemistry that we see in biology and in life outside the classroom. I'm going to end this chapter here.